We spend so much time in calculus 1 and 2 and before in the rectangular coordinate system, it feels like that's the only thing there is. But it's not true. And we will actually spend a lot of time in calculus 3 working with the polar coordinate system and a couple other systems that are developed from it. Now, why is this the case? Well, for starters, if we're taking the limit as we approach the origin, then it's actually frequently easier to do that in polar coordinates than it is in rectangular coordinates. In rectangular coordinates, you're letting both x and y go to 0. But in polar coordinates, what you're really talking about is the radius, just the radius going to 0 for some function. And that's kind of nice. It's a little bit easier because you're approaching from all paths simultaneously because it's just the radius. It doesn't have a particular angle given with it. So rather than having to look for specific paths, when you're doing it with polar coordinates, you're always approaching from all paths. So rather than using a specific path, when in the polar coordinates, we're always approaching from all paths. Because the radius is the ring that you're on. And if you're letting the ring that you're on go to 0, then you're automatically circling around, getting closer and closer to that particular thing. You might not even be swooping like that. I just think it's fun to draw it that way. But your radius is essentially shrinking. So let me pull up a Desmos graph really quickly. All right, so here I am in Desmos, which is a lovely two-dimensional polar coordinate grapher. And you can see that as I let r equals a, let me just slow down the speed a little bit. As I let my function r equals a get closer and closer to 0, so it's starting off at 5.5, and as it approaches 0, it's getting smaller and smaller and smaller, or vice versa, it's getting larger and larger, right? So if I let it be smaller and smaller, it will make the ring smaller. So I'm automatically approaching it from all sides, always. So it's shrinking it down. So it's not really a spiral, but spirals are fun to draw, right? But you're automatically closing in and honing in on that origin. Beautiful, huh? So that means that there's an advantage to using the polar coordinate system for this. All right, so let's see if that's the case. And of course, we all remember from whatever class we learned this in, usually calculus 2, if not before in pre-calculus, that x is equal to r cosine theta, y is equal to r sine theta, very much related to the unit circle that we learned in pre-calc, right? Except in the unit circle, it's always radius 1. And then x squared plus y squared equals r squared. Okay, so when we look at our particular problem, you can see there's an x squared plus y squared sitting in there, right there. And there's an x squared plus y squared sitting there. And according to up above, those are both r squareds. So I'm going to take the limit as r goes to 0 of r squared in the denominator. Now, what about the numerator piece over on the right? Well, there's a plus, and then x squared was r cosine of theta squared. So let me just kind of grab a pen here. So this one will be r cosine theta squared, right, because it's to the 2 power. And then we need another one for the y. So we'll have r sine theta squared. Okay, but that's the limit as r goes to 0 of r squared over r squared. So this is r squared plus. All right, this is going to become r squared cosine squared theta. So let me just write it that way. R squared cosine squared theta. And then multiplied by r squared sine squared theta. Okay, so that's the limit as r goes to 0. Sorry, my r got weird there. All right, I'm going to divvy this up just a little bit. Well, I guess I don't have to. Let me write it this way. R squared plus r to the 4th cosine squared theta sine squared theta over r squared. If you factor in r squared out of both of these, which you can, leave you 1 plus r squared cosine squared sine squared. Well, I still can't put 0 into this because I can't divide by 0. But I'm about to divide because r squared over r squared goes away. So that leaves you the limit as r goes to 0 of 1 plus r squared cosine squared theta sine squared theta. Okay, whatever cosine and sine do, they're both numbers between -1 and 1. So if I square them, they'll just become some number. So it'll be 1 plus r squared times some number, but the r is going to go to 0, right? This part right here is going to 0, which means this whole thing is going to be 0 because it's going to be 0 times something, whatever the something is, which means it's 1 plus 0 because you've got your 1 right here. So 1 plus 0, which is 1. Now let me really quickly show you the maple here. So there it originally is with the limit as I approach 0, 0, either with going to x0 first or with the y0 first. Here's y0 first. Here's x0 first. It doesn't make any difference. Now the three-dimensional plot of this is fascinating because this is what it looks like, right? And you can see we're definitely heading to 0, right? It's kind of swooping down to 0 from all z values as we approach that origin. And the origin is, of course, an empty hole because you can't have the origin as part of the domain. You can also find the limit this way, right, with x squared plus y squared, right, and letting it go 0, 0. That's another way to find that limit. And of course, you can also do it with r and theta also.